Okay, thank you. Okay, so one of the topics that I would like to talk about is subspace. One moment, let me change the display settings first. Okay, so for the first topic that we are going to look at now is subspace. From last time we were looking at vector space and also field, right? And we were talking about different properties in order to determine whether you have a vector space or not. So that was last time, and we also looked at a few examples of vector spaces. And if you remember from last time, we had different types of scenarios and examples for the vector spaces, ranging from just the typical real number planes, to polynomials, and all the way to the Galois field, right? Okay. So today we're going to look at first thing is the topic called subspace. Okay. So what is subspace? So if we take a look at what is called a vector space last time, so if you think about a vector space that has some type of a boundary, okay, and it has to have certain properties such as closure property, identity property, inverse, and so on. So when we talk about the subspace, let me change the color a little bit. So when we talk about subspace, I'll call it W, okay. So when we say subspace, members in W, okay, must be a subset of the members in the vector space of V, okay. So if we have W as a subspace, okay, the members in W has to be a subset. Okay, so in a way, the number of members in W has to be less than or equal to the number of members in vector space. Okay, or in a way, we can say that W is a subset of V, for example. Okay, since W is a subset of V, there are certain properties that it has to satisfy. Okay. And they will include the properties such as closure, okay, that we saw before. Last time, I think the property is property A1, AI from last time. We need to have the identity property, and from last time, I think it's A4. And specifically, last time we had this 0, as the identity. Okay, so this operation will be related to the addition. Okay, also we have inverse property, which is A5. This is from last time. Okay, so these are related to the addition. Okay, and the last property for the subspace is multiplication. Multiplication. Okay, and I think it's related to bi last time, and this one is the multiplication. Okay, and as you saw from last time, the property for addition or multiplication, they depend on your definition on the on what you will define. So let's take a look at an example of what do we mean by subspace. Okay, so let's take a look at an example. Okay, so let's say we have example number 1. Okay, so if I think about what is it? The vector space of a 3-dimensional vectors. Okay. So if we have a vector of x, y, z, and it is a member in the 3-dimensional real number space, let's call it R3. Okay. So this will be a vector space that we set up. Okay. Well, because it's a 3-dimensional vectors, so you can always think about the axis as x, y, and then z. Okay. And maybe there are some points that refer to x, y, z. Okay. And you can just draw it. So, what can be an example of a subspace? Well, an example of a subspace is, for example, is the R square. Okay. So if we have a vector of only x and y, okay, which is in R square, okay, we can typically say that the 2-dimensional real number space is a subset of the 3-dimensional real number space. Okay. So this is an example. So so this one is quite explicit, right? Okay. Let's look at example number 2. Okay. Let's say that we have a set of vector space and also the field V and F. Okay. If I let W to just consist of vector 0. So my question is, W, is it a subspace of V or not? Okay. So if you look back to the properties of the subspace, there are 4 properties that we have to look at. Okay. If W only has one member, okay, so if you look at the closure property, you have only one member here, which is 0. You add 0 to any 0, you get 0, right? Which is still in W, right? If you look at the identity, is there such an identity in this W or not? Well, here W only has one member, and it happens to be the identity for any addition as well. Okay. Thirdly, if you look at an inverse, well, an inverse of 0 is just what? It's just 0, right? Because they add it together, then they get 0. Right? And lastly, if you have 0, you multiply with 0, you get 0. Right? So we can say that this W, will satisfy all 4 properties. Okay, so we can say that W is a subset, which is a vector space is a subspace of V. Okay, so it's considered a subspace. Okay, so in general, if you want to test whether they are subspace or not, we can state the testing algorithm as follow. So let's say that given that W is a subset or equal to V, okay, so W is considered a subset of V if and only if, okay, or in short, we often write as if and only if, okay. If we can test that, well, x plus cy is a member of W, okay, where x and y is in W and C is in the is a field. Okay, if x and y they are vectors in W, and you can prove that x plus cy is always in W as well, then W is a subspace. Okay, then we can say that W is a subspace. Okay. Well, it turns out that this test incorporates all four properties already in there. So this is a general way to test it. Okay. And let's look at one more example for the subspace. Let's say this is example number 3. Okay. Last time we introduced one example that is, let's say that V has the elements of uh, 0, 1, 2, 3, okay, where we have, and also the field, okay, where we have the operation of addition and multiplication, but the addition is XOR, okay, and the multiplication is multiplication with modulo 2, okay. Can anyone tell me what this type of, how do you call it? What type of field is this called? When we have the vector space like that, and then we have the field like this, what do we call here? We call something field. Do you remember? Start with a G.
Galo field.
Yeah, it's a Galo field. Yes. Where P, where this is a prime number. Okay. A prime number. So if V is this vector space with the elements of 0, 1, 2, 3, so let me introduce a subspace. Okay. So let's say let's say I have that W has the elements consist of 0 and 1. Okay. And is W, so is W a subset of V? Well, certainly it is, right? And also, what other, well, if in order to answer this question, okay, so we have to check whether these elements in W, whether they satisfy 4 properties or not, okay. Or you can test with different different properties, right? Let's say number 1, which is closure. Okay. Well, I mean, you can test each properties separately, which are closure all the way to multiplication. Okay. Okay. Or you can test whether these elements they add up. You know, if they can, when they add up, whether they will be in the whether they will be in the W or not. Okay, there are two ways. So let's do it quickly. Okay, for some properties. No, let's say closures. Okay, if you add these elements, will they be in W always? Or if you do 0 plus 1, 0 plus 0, 1 plus 0, 1 plus 1, and 1 plus 0. Oh, it will always be in the 0 and 1 always, right? Okay. So you get all this as 0 and 1. So it's always in W, right? If you do multiplication, you have 0 multiplied with 1, 0 multiplied with 0, 1 multiplied with 0, 1 multiplied with 1. Well, it's always either 0 or 1, okay? So it's either 0 or 1. So it's also in W, okay? If you look at some other property like number 2, which is, I think property number 2 is identity, right? Okay. Let's say identity. Do we have an identity here? Do we have an identity here in W? Of course, it's 0, right? And for the property number 3, can we find inverse to all elements? What is an inverse for 0? And what is an inverse for 1? Inverse in terms of addition, okay? So what is an inverse of 0? What is added to 0 and gets 0? Thirawit, any idea? What is an inverse of 0 here? Meaning that 0 plus what? Get 0.
Any.
Second?
0.
Exactly, yeah. How about 1? 1 plus an inverse to get 0. So what is an inverse?
-1.
No, 1. Because this is XOR, okay? So you can look here. So it's a vector space with a Galois field, but W is a subspace, okay? It's actually is a subset of V, and it satisfies all 4 properties, okay? So when you do this, you have to be a bit careful on the definition of addition and multiplication. So in this case, addition means if you have A plus B, it is actually equal to A XOR B, okay? Or it is equal to A modulo B, okay? This is modulo 2, addition with modulo 2. Similarly, when we have A multiply or dot B, this is A multiply, let's say dot, no? So that is a bit easier to see. Let me put dot, okay? So it's A multiply B and then modulo 2. Okay? So that's what it means in such a case. Okay, so next topic for the first part, let's look at some of the concepts called column space and row space. Okay, they will be used a bit later when we talk about the general solution for a linear equation system. Okay, so let me talk about column space first. So what is a column space? Basically, it's just a vector space, okay, that is generated from column of vectors A, column of matrix A. Okay. So let me give an example. Let's say that I have that A is equal to a matrix, say it's 1, 3, 2, 1, and then 4, 7. Okay. So this matrix consists of 2 columns. Okay. So we can write it in terms of 2 columns or 2 column vectors. So A1 represent this column and A2 represent this column. Okay. And we write this with the notation that we always define a vector as a column vector, so that is easier to talk and to understand each other. Okay, and okay, so what is a column space? So column space, okay, as I said earlier, is a vector space that is generated from columns of A. Okay, so the column space is all the vectors C1 multiplied with A1 plus C2 multiplied with A2, where C1 and C2 they are the field. Okay, they're the element in the field. Okay, so what does actually means in terms of the geometric notation? Okay, so we for here each column has 3 elements, right? So we can consider each column as a 3-dimensional vectors. Okay, because the column space is the addition of 2 vectors, each one has 3-dimensional. Okay, so it means that the column space is how do you call it? Let's say that we have, let me change colors a little bit so that's a bit easier to see. Let's say that this is A1, okay, and let's say that this is A2, okay. So what can we get out of this column space? Maybe let me change the color again one more time. Let me do, let me see, let me use the green colors, okay? So the columns, oh, this color is a bit hard to see. So the column space is just the, how do you call it? The planes that you generated, okay? From these 2 vectors, you know, that you can construct. So this is called column space. Okay. So you notice that in such a case, when you add the column space from 3-dimensional from 3-dimensional columns, what is the dimension that you get? For this, we call this as plane, right? They are not volume. You know, if we talk about volume is like 3D, right? But here we have planes. Plane is just 2D, only 2-dimensional. Okay. So it means that the column space for the 3-dimensional columns, the column space is actually like 2D planes. Okay. Okay. And if I write these in terms of the multiplication, what do I get? C1 multiplied with A1, vector A1 plus C2 multiplied with vector A2. I can write these as A1 and A2 and multiply with C1 and C2. Okay, you agree if I write it like this? Well, it means that I can write the vector space as, so this part is just the matrix A, right? And multiply with C1 and C2. Okay. So if you write it formally, we will have this. Let me go to the next page, okay? Do you finish? If you don't finish, please tell me, okay? Okay. So when we say column space, okay, let me use the notation like this. Okay, it's a strange look, you know, but it's just a C actually. Okay. So let me give a very formal definition. Okay. So let A be an m by n matrix. Okay. Whose columns are A1, A2, all the way to the nth columns. So I write it as AN. Okay. The column space or C of this matrix A is equal to the set of C1, A1, plus all the way to Cn, An, where C1 all the way to Cn, they are just numbers. Okay, so they are field elements. Alternatively, equivalently, we can write it as a set of A multiplied with C1, C2, all the way to Cn. Okay, where C1 all the way to Cn, they are just the elements in the field. Okay, so this is like a formal definition. Okay. Okay, so let's take a look at an example of what we can generate. Okay, actually, let me take a look. So previously, okay. Okay, example. So let's say that given that A is equal to 2, 2, 1, 0, 2, 2 matrix. Okay, let's say that we are asked to find the column space of A. Okay. Also remember that I said from the beginning of the class that when we print it or type it, we always if we consider the IEEE format, we often write the matrix and vector in the bold phase. Okay. However, when writing like on screen or on paper like this, in order to distinguish between variable real numbers and the vectors matrices, I often put an underline, okay, so that we can distinguish between the real elements, the variables, and the vectors matrices. So for this example, let's say that a matrix is given a matrix A is given as 2, 2, 1, 0, 2, 2, okay? And we are asked to find the column space of A. So what do we get? Well, so the column space of A is actually, if we do it from scratch, we can just add up the each individual column, right? But in this case, because we notice that column number 1 and column number 3, they are identical. I guess so. In this case, there's no need to duplicate column 1 and column 3. Okay, so it means that in this case, the column space is C1, 2, 2 plus C2, 1, 0. Okay, where C1 and C2 or Ci, where I is equal to 1 and 2, they are just a field element. Okay. So we can just say this, okay? Or if you want to write it out very explicit, we can write it as a C1 times 2, like that, and then plus C2, 0, okay, which is equal to 2C1 plus C2 and then 2C1. Okay. So for any numbers, C1 or C2, if you replace with numbers, then you can get the whole column space. Okay. let's say you say C1 is 1, C2 is 2, let's say minus 2, okay? Then you will have this as a, what is it? What do we get? 2 minus 2 is 0, right? And 2C1 is just 2, okay? If you change number, you get different vectors. Let's say C1 is 2, C2 is 3, just for an example. Then we have what? 2C1, which is 4, 4 plus 3 is 7. And then 2C1, you get 2. Okay. So that's all. Okay. Okay. So this is an example. And similarly, we can define the row space as well. So we have the column space, and now we have row space. Okay. So for the row space, we will define it differently. So for row space, let me give you the same matrix, which was 1, 3, 2, 1, and then 4, 7. Okay. So in this case, we can write it as a set of different rows of A. Okay. Let me see. Should I use a small a as well? Maybe I can change. Let me write it as R so that they are not the same. Okay. So let me write it as R1. But then because for each row, when we define a metric, a vector, we define as a column vector. So we will write R1 as R1 transpose. Okay, R2 transpose and R3 transpose. Okay. So this is a formal way of writing, where R1, R1 will be equals to 1, 3. Okay, R2 is equal to 2, 1. And then R3 is equal to 4, 7. Okay. So don't get confused when you see some definition like this. Okay, it's just to conform to our definition of vectors. Okay. So when we talk about row space, what is a row space? Well, a row space is the same as a column space. So for the row space, is the vector space that is generated instead of columns, right? Now they're generated. The vector space is generated by the rows of the matrix A. Okay. Therefore, so for the row space. Okay, so it's a set of, in this case, it's a set of C1 C1 multiplied with row number 1 okay, plus C2 multiplied with R2 transpose plus C3 multiplied with R3 transpose. Okay, so it's a set of these generated vectors, so-called vector space, where C1, C2, and C3, they are the element in the field. Okay? And in this case, it's probably just a real number. Okay. And let me see. So in this case, it means that it's a set of C1 multiplied with 1, 3, plus C2 multiplied with 2, 1, and then plus C3 multiplied with 4, 7. Okay. And equivalently, you can write it as C1 multiply with C1, C2, and C3, and multiply with R1 transpose, 2 transpose, and R3 transpose. Okay. So this whole thing can be written like this, which is equal to C1, C2, C3 multiplied with the matrix. Okay. So, so the formal definition for the row space will be similar to the column space. Okay. In that, for the row, if can you follow? If you don't finish the previous page, please tell me. Okay. So for the row space, let us represent as a R like this. Okay. So we will define it similarly to the column space. So let A be an M by N matrix. Okay. Whose rows are R1 transpose, R2 transpose, all the way to R what? R what? M or N? Because now we talk about the row, right? So we only have Rm transpose, okay? Then the row space of matrix A is given to the set of vectors. You can write it two ways. One is R multiplied with R1 transpose plus C2 R2 transpose plus all the way to Cm Rm transpose, where Ci is the field. It's an element in a field. Okay? Or equivalently, you can write it as if you look on the previous page, the order will switch compared to the column space. So now you will have, okay, now you have a C1, C2, all the way to Cm, and multiply with A, okay, where Ci is an element in the field. Okay. So these are three concepts: subspace, column space, and row space. Okay. Actually, since we have time, let me look at one more type of space, and this one is called the null space. Okay. If you don't follow the lecture or you haven't finished writing, please tell me. Okay. So the last one for the first part is called null space. Do you know what null means in English? In Thai, in English, you know what null means? Can you guess what null means? Can you guess, Thanat?
It's been nothing.
Say again?
Nothing in that space.
Exactly. Actually, it means zero. Zero. In this case, no. So, okay. So it's a null space. Okay. So let matrix A be an M by N matrix. Okay. So previously we set A as an M by N matrix, and we can generate the column space and also the row space, right? So now let A be the same matrix, okay? So if we have the set of any vectors x of vector x, such that A multiplied with x is equal to 0, okay? Then x is called null space. Okay? So, how should I give an example? Well, let's say, look at an example, okay? let's say that A is an example which is let's say 1, 2, and then 2, 5. Okay. Okay, and then I say find null space. Null space is often represented by n like this, and then matrix A. Okay. So find the null space of A. Okay. So for this example, we will start like this. We set AX is equal to 0, okay, which is 1, 2, and then 3, 5. Okay, times x. Let x be x1 and x2, okay, equal to 0. This 0 is a vector, okay. Okay. So we can do it from very simple way. There are two ways to do it. If you have large matrix, you can do Gaussian elimination, and then you can find x1 and x2. If you have very small like this, let's just do it. No. So we have first equation x1 plus 2x2 is equal to 0, and then second equation we have 3x1 plus 5x2 is equal to 0. Actually, sorry, let me do this so that is a bit easier, no, for you. Okay. Let me do 0 like this, because sometimes there are many solutions. Okay. Well, in this case, you find that x2, because 5x2 is 0, so you have x2 is 0, right? And if x2 is 0, it means x1 is also 0. So here, actually, in this case, there's only one solution. So null space of A is equal to 0. Okay. In the following example, we will look at the case where you can have many solutions that have that makes A to be 0 when multiplied with AX. Okay. Let me see. Maybe I have another example that is a bit more precise. Okay. I can use this. Okay. Let me do one more example. Okay. Okay, one more example. Okay, so let A to be 1, 0, 1, 0, and then 1, 1. Okay, so find the null space of A. Okay, so previously on the previous example, we only have one solution, right, which is 0 and 0. In this case, we have A, which is a 2 by 3 matrix. Let's see what we can find. Okay, so I'll do the same thing. So I have 1, 0, 1, 0, and then 1, 1. And then I multiply with the X matrix, X vector. Let me write it as x1, x2, and x3. Okay, and I need to set it so that it's equal to 0 and 0. Okay, so I have two equations here. Okay, can you tell me the first equation? Panatson, can you tell me the first equation from this?
x1 plus x2 plus x3 equal to 0.
Okay, yes. And Pio, can you tell me the second equation?
Yes, x3 equal to 0.
Yeah, you multiply each element, right, with the column.
Yes.
So you get x3 equal to
Equal to
0.
0.
Okay. So when you combine these two together, you have that x3 has only one value. It is possible, right? Therefore, from 1, so I have x1 plus x2 to be 0, right? Because x3 is 0. In other words, x1 has to be equal to minus x2, okay? Therefore, it means that the null space will be equal to the set of let me call it as x, no? X minus x and then 0, okay? Where x is an element in the field, okay? So any vector that satisfies this condition, like 1 minus 1, 0, okay? Or, you know, minus 2, 2, 0, and etc. When these vectors multiply with a matrix, you always get 0 vectors, right? Okay, so it means that these are all the elements in the vector space that satisfy Ax equal to 0, and we call it null space. Okay, so formally, formally for null space, we will define it as n of A, okay, equals to all the x vectors in R to the n. R to the n means there are n elements, okay, or we can call it n tuple vectors, okay, such that A multiplied with x is equal to 0 vector, okay, where A is an m by n matrix, okay. Yep, that's it. Okay, let me give another example before we have a short break. So for some students who work with the area of error correction codes, okay. So in error correction codes, let's say we talk about linear code, right? Okay. Generally, in order to generate the codes, you multiply the message vectors with the generator matrix, right? And then you get codes, which is m multiplied with g, okay? So we call this as the code is generated by the column space, okay? It's the column space of G, okay? And that's why G is often called the generator matrix, okay? And on the other hand, for a given generator matrix, often there's another matrix called parity check code matrix. Okay, if you don't work with error correction code, don't worry yet. There's gonna be for a specific for any valid code word. Okay, you see multiply with H transpose, you get 0 vector. Okay, or you can write it as H multiplied with C transpose is equal to 0 transpose. Okay, and so in a way, this C transpose is the null space of H. Okay. So when you read some research related to linear error correction code, don't you often hear the word like column space, row space, and null space. Okay, so just keep that in mind. And what is important in terms of the use of the null space? Okay, so this is the last slide. Okay, so if I am given a linear equation, Ax is equal to b, okay, where the A matrix is the a matrix with all the coefficients, okay. X is the unknown, and B is also the known values, okay. So we can say that X is in the column space of A, okay. And sometimes we can find a y equal to 0, where y is the null space, okay. Okay. Suppose that x0 is a solution of Ax equals to b, such that Ax0 is equal to b, okay. So if I add up x with c multiplied with y, okay, this will be also solutions to the equation Ax is equal to b, okay. They are also solutions, okay. And this is because if we multiply A and x plus cy, okay, remember that x is, in this case, x0 is a particular solution, and y is the vector in the null space, okay. If I expand it, I will get a x0 plus c ay, okay. Because I know that C is the null space of the A, then this is 0. It means I have this is equal to B. Okay. So this will be our approach in computing all the solutions for a general linear system. Okay, so let's have a like 5 or 10 minutes break and then come back. Okay. So whoever who's recording, please just stop now, and then we record the next session when we start. Okay.